In this lecture, we'll learn about the pumping lemma for regular language using a train journey analogy. How to find out the language L is not regular. In that case, it cannot be accepted by finite automata. So the pumping lemma for regular language helps us to prove that the language is not regular. Remember one thing, pumping lemma does not help us to prove that a language is regular, but the other way round. Instead of starting with the formal theorem, we shall build the intuition first using the train station analogy and then connect it to the mathematics. Before we learn the pumping lemma, let us understand why such theorem exists. Imagine you are traveling on a train. Your train passes through a series of railway stations. Now imagine there are only 4 stations on the route. Let's call them station 1 A, station 2 B, station 3 C, and another station 4 named D. Now suppose I tell you that the train makes 8 stops before reaching its destination. Can the train visit 8 different stations? Think over it. Of course not. There are only 4 stations available. Sooner or later, the train must visit one of the stations again. This simple observation comes from a famous principle in mathematics called the pigeonhole principle. Now replace the train with a finite automaton and we'll see replacing the stations with the states. If the automata has only p states but it reads a longer string longer than the p symbols, it must eventually revisit a state, and that repeated state creates something extremely important, and that is called a loop. So let me ask you a question. If a DFA has 5 states and the input string has 20 symbols, do you think the DFA can avoid visiting the same state twice? No, a repeated state is unavoidable. So in this pigeonhole principle, if more objects are placed into a fewer containers, then at least one container must contain more than one object. In our example, the stations are the containers and the train visits are the objects. Since there are more visits than the stations, at least one station must be visited more than once. Let's see what actually happens. Suppose the train moves like this: station A to B to station C, station D, back to station B, station C, station B, and finally station D. So if we have to visit 8 stations before reaching the destination, and the constraint is physically there are only 4 stations, then we notice something interesting, that everything between the first visit and the second visit forms a loop. This loop can be traveled again and again. Now think like a computer scientist. Each station represents a state of a DFA. So whenever the DFA visits the same state, it means the machine has forgotten exactly how it arrived there. It only knows that it is back in the same state. Therefore, it can repeat the journey again without changing its final behavior. That repeated journey is exactly what the pumping lemma calls the substring while. So the key message is a repeated state always creates a loop, and every loop can be traveled multiple times. So now comes the exciting part. Suppose our train reaches the station B and starts traveling around the loop. Can the train go around the loop only once? Yes. Can it go round twice? Yes. Can it go round thrice, 10 times? Absolutely yes. So no matter how many times it travels around the loop, it still reaches the destination D. This is exactly why we call it pumping lemma. We are literally pumping the loop. Imagine stretching a spring. You can stretch it once, twice, three times, or not at all. So sometimes the I equal to 0. That means you have not done a loop at all. So the beginning of the journey remains the same. The destination remains the same. Only the number of trips around the loop changes. So looking at these four journeys, there can be 0 repetition, 1 repetition, 2 repetition, nth repetition. So although the journey lengths are different, the train always reaches the same destination. Similarly, a DFA still accepts the string. What happens if I repeat the loop 100 times? Does the DFA get confused? No, because it returns to exactly the same state and the same destination. Now let's connect our story with the mathematics. The train journey corresponds to the string W, that is the total length W, equal to X, Y, and Z. Look at the rectangle with the colored sections X, Y, and Z. Let us understand each part. The first part, green in color, is X, is the journey before entering the loop. The second part, Y, is the loop itself. The third part, Z, is the remaining journey after leaving the loop. Now let's match each condition of the pumping lemma. First, the length of the xy is less than equal to p. What does this mean? The loop must appear within the first p states. Why? Because before reading p symbols, the DFA has already visited enough states that one must repeat. Secondly, the length of y should be greater than 0. The loop cannot be empty, otherwise, there is nothing to pump. Finally, the generalization x y to the power I z belongs to the language L. This simply means we can travel around the loop with I equal to 0 and I greater than 0. So any number of times, and the resulting string is still accepted. The mathematics is simply describing the same train journey we have just understood. So, what have we really learned today? The pumping lemma is not magic. It is simply a consequence of one important fact. A finite automaton has only a finite number of states. So, whenever the input becomes sufficiently long, the automaton must revisit a state. A repeated state creates a loop. That loop can be repeated, removed, or traveled multiple times without changing the acceptance of the string. That is why every regular language satisfies the pumping lemma. But here's an important point. We rarely use the pumping lemma to prove that the language is regular. Instead, we use it to prove that certain languages cannot possibly be recognized by any finite automaton. In our next example, we'll use the pumping lemma to prove that the famous language L is equal to 0 to n, 1 to the power n, where n greater than equal to 0 is not regular. And you'll see finally the true power of this theorem. So let us prove this language L, 0 to the power 1 to the power n, is not regular using the pumping lemma. So notice the rule. Every string has, so these are the examples of the some of the strings from this language which will be accepted. So zeros come first and followed by all the ones, and the number of zeros are equal to number of ones. Can a finite automata recognize this language? We are going to prove that the answer is no. What information would the DFA need to remember? Would it have to remember how many zeros it has seen? Yes. And that already sounds difficult because DFA has only finite memory. In mathematics, many proofs begin with an assumption. So let us assume that this language is regular. If it is regular, then pumping lemma must hold. That means there exists a pumping length P, such that every sufficiently long string can be pumped. So, assuming that the language is this language L is regular. So, the pumping lemma allows us to choose any string in the language, provided its length is at least P. Which string should we choose? We choose the simplest possible one. W is equal to 0 to the power P, 1 to the power P. Because it belongs to this language, it has exactly P zeros followed by P ones. So what is the length? Length is 2P, which is certainly greater than P. Therefore, this string satisfies the pumping lemma. So demonstration like 0, 0, 0, if 10 zeros we have and 10 P's we have, so then we have 20, 20 of them. So now the pumping lemma says the string must be divided into W equal to X, Y, Z. But there are three conditions. The important one is X, Y length should be less than P. Remember the first P symbols are all zeros. Therefore, both X and Y must lie completely inside the block of zeros. Neither X nor Y can contain any ones. So here can Y contain a 1? But here once we have all the zeros in the xy, we won't have any 1, and because xy is less than equal to p, we haven't reached the ones yet. So here if you are having 0, 0, 0, 1, 1, 1, so we are considering that xy, which is having the loop, this is xy, is less than equal to p. Okay, but we know that p, there are p zeros and p ones. Okay, so here if I break it or if I loop it, every time there won't be any ones, it will be only the zero as a value. So either the number of zeros will shrink or the number of zeros will be increased. So if it is shrinking or increasing, the number of p's with ones will not be equal to the number of zeros. So after removing the y, so there is actually x, we have seen here, that is the formula x y to the power I and z. So when I equal to, we don't have, we have just the xz, or if it is, it's always 0, xy, this part is always 0 and this part will be 1. So if you increase pump, if you pump the y part, that is the y substring, once, twice, thrice, it will always add the zeros, but this part won't have any ones, and that's how uh, the number of zeros will never be equal to that of the number of ones using the pumping lemma. So we reached a contradiction. The pumping lemma says every pumped string must remain inside the language. But after removing y, our new string is not inside the language. So what is the sequence of proof? Assuming this is regular, choose a long string, divide it into x, y, z. Observe the y contains only 0. So removing y, the resulting won't have the equal number of zeros and ones. So that's how it contradicts that the language is not regular. So let us have another story analogy where we will see that this particular language is not regular. So here this is actually a code 01 with a code. Can a finite automata recognize the language? So here Leo is a librarian with a finite memory, a tiny memory. He has to approve any book which comes with this condition that 0 to the power n, 1 to the power n is satisfied. So people bringing him a very special type of record. So that record contains first sequence of zeros followed by a sequence of ones. So his job is very simple. He must approve the record only if the number of zeros is equal to the number of ones. So when it is three zeros, three ones, he is happy and he stamps uh, and it gets accepted. But he cannot remember a very large number of zeros and large number of ones. Okay, so then it becomes a big problem. So he is like a finite automata. He cannot remember an unlimited amount of information. So what happens if someone gives him a record of 1000 zeros followed by 1000 ones? Can he remember exactly how many zeros he has seen before he starts counting the one? No, he starts forgetting. So that's what we are saying. A DFA has only a finite number of states. It cannot count forever. It cannot remember arbitrary large numbers. And that is where the pumping lemma enters into the picture. Instead of directly proving that Leo cannot do his job, we must first assume that he can, and then our assumption leads to a contradiction. So here we remove the xy, the mathematical explanation can also come here. What we are pumping the substring. So once we pump or remove it completely, what happens to the language? The language has the total number of zeros less than that of the P. So the first P symbols are always 0. So therefore y must consist entirely the number of zeros. So this single insight is the heart of the proof. Once you understand that the first block of zeros are contradicting with that of the number of P's. So the real problem is not the zeros or ones. The real problem is the equality. A long enough journey through a finite number of states must create a loop. That loop is what we pump, and that simple idea forms the foundation of the pumping lemma. Thank you.